Hello everyone, my name is Mark Hildebrand, and today I'm going to be presenting our work, A Case Against Hardware-Managed DRAM Caches for NVRAM-based systems. As an executive summary of this work, we're trying to understand the performance of large DRAM caches for terascale NVRAM-based servers. These are servers that have terabytes of NVRAM or persistent memory and hundreds of gigabytes of DRAM. To understand the workings of these caches, we developed a series of micro benchmarks to study the performance implication, and then we also perform a couple of case studies with real applications to further gain an understanding. And we find that the direct map policy of this cache in particular can lead to a high miss rate, and that under a high miss rate, there's a significant bandwidth reduction. Additionally, there's also a potential to emit many unnecessary dirty writebacks, which further reduces performance. So let's kind of motivate why these DRAM caches are a thing. So it's no secret that applications are just growing with time. Recently, in the language model realm, OpenAI has announced a model that has 175 billion parameters. So you're talking hundreds of gigabytes just to store the model itself. Now, because these models are also used in high-performance situations, they need to be kept in a relatively fast memory. Like, you can't just put them on an SSD. But DRAM is really expensive. So to help kind of amortize this, persistent memory or NVRAM-based servers are starting to become more common, with the most common type of persistent memory being Intel Optane DC, or data center. Now, this is cheaper per byte than DRAM. It has orders of magnitude more capacity, so a single one of these DIMMs that you see here can have up to 512 gigabytes. And it is also byte addressable, so unlike, say, an SSD that you have to access in blocks, you can access these devices at a much finer granularity. The downside is that there's an increased latency and decreased bandwidth with these devices with respect to DRAM, so they can't just be used as a drop-in replacement. And additionally, to actually use these devices often requires changes to the underlying application. So to help promote adoption and lower the barrier for entry, these servers can be configured in what's called 2LM, or memory mode. Now, in this mode, the NVRAM is used as the system memory, and DRAM acts as a transparent cache. DRAM caches have also been extensively covered in the literature. Now, the big problem with a DRAM cache is maintaining the metadata, so like the tags and the physical address, etc. And so a lot of these previous designs explored different ways of doing clever tricks to make operation efficient. The problem with this particular cache is that it's significantly larger than caches that have been studied in prior works. So it's on the order of like 192 gigabytes, which at that size, clever tricks for managing metadata becomes impractical. And so I mentioned that there have been a couple of software attempts to more efficiently use the slower persistent memory. So one of these is AutoTM from our group, which focuses on CNN training. The idea there is to use the static information about the training graph to optimize the location and movement of intermediate data. And we were able to achieve a 3x performance improvement over the 2LM hardware cache. Another example of clever software outperforming the cache is from Sage. Now, this is a framework that's targeted mostly towards graph analytics. And the trick that they use is they only use the persistent memory as a read-only data structure. And any mutation that has to happen during the course of their algorithm happens only in DRAM. And as a result of this, they're able to get an almost 2x speed up over a different framework running in 2LM. And so the question we want to answer is, why? Now we'll talk a little bit about the general performance characteristics of the cache. To understand the bandwidth implications of having to maintain this metadata and the extra access amplification that this incurs, we wrote a series of high-performance kernels to generate custom load and store traffic. And the idea here is that if you use these load and store traffic over a small array that fits in the DRAM cache, then every access will be a hit. And if you use a really large array that is over twice as big as the DRAM cache, and make sure that you access each index exactly once per iteration, then you ensure that each access is a miss. In addition, we use the hardware performance counters found on the memory controller on these CPUs to give us an idea of how much traffic is being generated to DRAM, how much to persistent memory, the breakdown of read and write traffic, etc. So I'm going to talk a little bit about these micro benchmarks. So the idea here is to generate really high performance load store loops, and we use Julia's metaprogramming capabilities to generate these loops. So you can see an example inner loop right here on the side. Choices that we can do to control this are we can change the AVX vector size, so that can be 128 bits, 256, 512. We have the option to emit either standard or non-temporal loads and stores. This example here is read, modify, write loops, and so you can see there's a load followed by an addition and then a write back. And finally, we also have the option to statically unroll these load store loops a little bit. So here you can see this is unrolled 4 times to give an access granularity of 256 bytes. But we also have the option to unroll it 8 times if we want, or 16. Other knobs that we have are we can vary the number of threads, we can change the size of the underlying array. We can also access these arrays either in a sequential or pseudo-random pattern. In the pseudo-random pattern, we make sure that we touch each index exactly once. So what we found as a result of performing studies with these micro benchmarks is that there's a significant access amplification in the cache. Now there's access amplification due to having to write back dirty data from DRAM to persistent memory, or extra movement there just required to maintain consistency. One thing we want to point out is, in particular, dirty write misses suffer from really high access amplification, with 5 total accesses to DRAM and persistent memory for a single write coming out of the LLC. We also found that even in the best circumstances, so this is with sequential traffic, so even in the best circumstances, we're only able to achieve a fraction of the achievable bandwidth if you're writing and reading directly to the persistent memory. And so this is in the best circumstance, and so we expect that if there's a high miss rate in the cache, you're going to have a very severe bandwidth bottleneck. In particular, as it comes back to dirty misses are very expensive with a maximum bandwidth of only 8 gigabytes per second, again, in the ideal case. So from these micro benchmarks, we've learned a couple of things. We've learned that there's up to a 5x access amplification per demand access, and so there's a lot of extra bandwidth that's being used in the system. And with high miss rate, there's going to be poor bandwidth utilization, not even accounting for the higher latency of persistent memory. Now, it is possible that future implementations of this DRAM or this cache can fix these issues, but there are other more subtle pitfalls that this cache falls into that we'll talk about now. So in our paper, we performed 2 case studies, one on graph analytics and one on CNN training. Now, my co-author Julian gave a talk on the graph analytics a couple weeks ago for the Non-volatile memory conference, so I will be focusing on the CNN training here. So why study CNN training? Well, for one, these models are getting huge. As I talked about in the beginning of this presentation, the recent GPT-3 has 175 billion parameters, and we expect that models are just going to get larger over time. Second, DNN models also have fairly predictable memory access patterns, which means you can pull compiler tricks that you can't necessarily do with normal programs. And so our previous work on AutoTM modified the in-graph compiler to use profile-guided optimization to control the placement and movement of intermediate data. And using this kind of clever scheme, we were actually able to outperform 2LM by a factor of 3. So now I'm going to so in addition to the lower bandwidth that we talked about from the micro benchmarks, there is actually another phenomenon going here that I want to describe. But to do that, I have to first talk a little bit about how DNN training works. So the idea behind DNN training is that there are trainable parameters for the model, and you feed in the input, and there's computations. Basically, the model is executed forward just as it would be normally. Now, the output of the model is compared with the expected result to generate a loss, and then there's the backward pass, which computes the gradients of all of these trainable parameters. And these gradients are used to update the parameters in a way that's going to minimize the loss. Now, to make this computation a bit more efficient, it turns out that it's helpful to store intermediate results during the forward pass for use on the backward pass. And so that this means that throughout an iteration of training, so an iteration of training is one cycle of forward pass and backward pass. So through an iteration of training, the memory requirement grows up until the end, and then it shrinks again. So in particular, we used 4 different DNN networks, and we scaled the batch size so they had a really large memory footprint to greatly exceed the size of the DRAM cache. And again, we used hardware performance counters to monitor bandwidth between persistent memory and DRAM. So when running Densenet, so Densenet's the most interesting one to look at. So when running Densenet under AutoTM, we see the bandwidth breakdown looks like this shown. The forward pass happens up until timestamp about like 85, and then the backward pass. And the bandwidth looks reasonable, right? Like during the forward pass, that intermediate data is getting generated and it's getting written to persistent memory, and then on the backward pass, it's just being read. 2LM, on the other hand, looks like this. So you can see that the bandwidth overall is considerably lower, and there are NVRAM writes on both the forward and the backward pass, and that there are a couple of regions of really high bandwidth at the beginning of the forward and beginning of the backward pass. Essentially what's happening is the same phenomenon occurs on the forward passes with AutoTM. We're generating intermediate data and it's getting evicted and put back into the cache. But on the backward pass, the same thing is happening. You see, the cache is not smart enough to know that the data that we're accessing is actually only going to be written to in the future and not read. So as a result, there is significantly more dirty writebacks that happen to the cache, which, as we've seen previously, just completely tanks performance. So the takeaways is that this DRAM cache does allow for quick adoption of the large capacity offered by persistent memory. But its utilization is low, especially for applications with low locality, which are exactly those that would take advantage of having this much memory. And we also know that dirty writebacks are really expensive and should be avoided at all costs. And finally, because hardware doesn't know if memory is free or not, semantically speaking, with respect to the program, it always has to be conservative. And this can result in a lot of extra traffic that's not strictly necessary. Now, software solutions aren't the end-all either. For one, if software is used to move data between persistent memory and DRAM, then you have to use CPU cores to do this transfer. And that means you are losing cores to do compute, and you also lose the ability to move data asynchronously, or at least as easy as it could be with hardware. And in addition, it requires really specialized knowledge of your application and data use patterns. And so things like AutoTM or Sage don't really generalize to other applications. The ideas behind the cache do, but the techniques themselves don't. And so the question I kind of want to leave you with is, all right, what can we do to do this better? We want the high-level knowledge of software to take advantage of things, like avoiding unnecessary dirty writebacks. But we also want the benefits of hardware, the asynchronous data movement, the automatic managing of everything. And so how we do this is, a really good question for future work. So I'd like to thank our sponsors at the Intel Corporation, the NSF, and the members of the Davis Computer Architecture Research Group. And I want to thank you for listening to this presentation. Thanks.